Now, for Chapter 5, I didn't show you the front page of Chapter 5, so let's set up a new protocol here by showing the front page of Chapter 6. This deals with rational expressions, and a synonym for rational expressions would be fractions that involve variables and this type of thing. And then equations that have variables in the denominator and everything. And of course, we'll tie it into function notation. Here's a question. How long does a heart last? In generals, animals have higher heart rates, have shorter lifespans, as shown by the graph. In example 10 of section 6.8, we use the given data to estimate the average lifespan of a cat. Okay, so where is the cat here? I don't see a cat. Oh, maybe, is that a cat? I don't know. Anyway, it'll tell us. Now, there are 8 sections, but we only do 5 in Chapter 6. We're doing 6.1, 6.2. We skip complex rational expressions, which is actually one of my favorites, but it's not in our curriculum. We do rational equations. We do applications, that is, those word problems. Now we skip division of polynomials and synthetic division, which again are kind of important topics, but they're skipping them. And then we do formulas, applications, and variations. So of the 8, we do 5. So, like fractions in arithmetic, a rational expression is a ratio of 2 expressions. That's one on top, one on the bottom. In this chapter, we simplify, add, subtract, multiply, and they do divide, but we're not going to be doing that. We then use these skills to solve equations and applications involving rational expressions. So as we start topic 1, we're going to look at rational expressions and functions. We're going to multiply and divide. Now this is a little different division than what would have been treated in topic 6.6. This is a more simple division, as you will see. Now, a rational expression consists of a polynomial, that would be in the numerator, divided by a non-zero polynomial. Now, keep in mind that they had said that you're not allowed to have variables in the denominator and call them polynomials. So here they're loosening the definition a little bit, and they haven't ever explained that to me to my satisfaction, but we'll let it ride. Okay, so let's get started. As you see, these are all fractions. And again, we call them rational expressions. Now, functions described by rational expressions are called rational functions. Following is the graph of a rational function. Here we have the function of x is such that 1 over x. And if you put that into your calculator, made this a y, your graphs would look like this. Okay? So graphs of rational function vary widely in shape, but some general statements can be drawn from the graph above. Graphs of radical functions may not be continuous. As you can see here, these are not continuous. There's a gap there in the middle. That is, there may be a break in the graph. And this one is the one they're illustrating, consists of two unconnected parts with a break at x equals 0. X will never equal 0 here. The line never quite reaches the 0. Now, the domain of rational functions may not include all real numbers. For instance, in this domain, and again it's 1 over x, can x ever be, let's look at it right here, can this x ever be a 0? No, because we say that is undefined. That's why the domain of this function would be all real numbers, but x cannot equal 0. We'll be treating that as well as we go on. Okay, let's look at this carefully, and I will make it a little smaller so we can fit it in there better. Now, here we have a function dealing with time, and h is hours. And they're saying the function given by this rational expression gives the time in hours for two machines working together to complete a job that the first machine alone could do in t hours and the other machine can do in t plus 5 hours. How long will it take the two machines working together require for the job if the first machine alone would take 1 hour? So here we're introducing time now, which is our t, as 1 hour. So we substitute it into this rational expression, and there the work is all there. And when they get to the end, and remember you have to do this multiplication first, order of operations, we end up with 6/7 hours. Now, in defining the domain of this, what value, and let me get my pen going here, would make our denominator a 0? And we had done some like this before. So that then becomes 2t equals a negative 5. T equals a negative 5/2. So for this denominator, we would say t could be any real number, but t could not be a negative 5/2. And that's what they're saying here in set builder notation from the old days, and then to put it in interval notation from the old days as well. Let's continue. Example 2. Find the domain of the function given by this. Well, again, our basic technique, and we've done these already, would equate the denominator to 0, factor the denominator, and find out which values of x would make our denominator a 0. And we see if x were 5, if x were a negative 3. So our domain then of this rational expression is x is any real number, but x cannot be a 5, nor could x be a negative 2. And we did one like that in an earlier lesson. And if you recall, this was the set builder notation, and this was the interval notation. All right, moving on into the mechanics of this now. They want us to simplify rational expressions and functions. Now, we know we can have a fraction, and if we multiply the fraction by 2 over 2, which is actually 1, we can multiply anything by 1, not change its value. But if our 1 is in the form of 2 over 2, this fraction becomes 6/10, which actually represents the same number. We say the 3/5 form of it, though, has been simplified, and that's what they're working on. And you simplify by factoring the top, factoring the bottom, and removing any ones that appear. 2 over 2 is 1. And when we cancel those out, we end up again with the simplified form. So, when we have rational expressions that look like this, and remember they may have been a trinomial that we factored into this, we're looking for common factors that we have over here. This over this is 1. So simplifying this, you factor it and then cancel out common factors. Okay? And whether it's written in a function format, it works the same. Now, what would be the domain of this? Now, we run into a problem, and we can see it starting here as f of x is this, and g of x is this after we've simplified. So the domain of this would be all real numbers, but x cannot be a negative 2, x cannot be a negative 3. But if we cancel these out and simplify, here we would only say x cannot be a negative 2. So we have to be careful about this depending upon what they're asking us. So the domain of f, as we said, was this, all real numbers but not these. Domain of g is all real numbers but not this. Thus, as presently written, the domain of g includes a negative 3, but the domain of f does not. This problem is easily addressed, and again, this is critical, by specifying that you have done the simplification, and then you are saying that x cannot equal a negative 3, because we know that this one, x cannot equal a negative 2. Again, when I give you a test, I'm not going to be so picky and trying to trick you when you're doing something like this. It's just something to be aware of. Okay, example 3. Write the function given by this. And as you look at it, what would the strategy be? Well, they have it all listed down there, but I like doing these once in a while. What we're going to do is factor a 7t out of this top one, and I get t plus 3. And what do we do with the bottom? Well, we can factor out a 7t times 2. And what do we notice now? We have a common 7t that we can factor out. And that's our answer. They're doing it in a few more steps here. Now, keep in mind also that your t cannot be equal to 0. Okay? All right, next page. They get a little more challenging. And more information on this. All right, example 4. And what do we do there? They want us to simplify. So when they say simplify with rational expressions, they're really meaning factor and cancel out common factors. So no common factor there, we're just going to factor this. X, 5, 3, plus minus is the top. And then we have 2x, x. And again, I have a little experience in this. This is going to be negative, and this is going to be plus. Now, as we look at that, oh, I think I put the wrong one up there, didn't I? Yes. The difference is 3, but when we factor, it's supposed to be a 2. You're hoping to find something that will cancel out. Sorry about that. So this cancels with this. Now notice you end up with this over this, but when you're stating the domain, equal each of these to 0. Here this is going to be a negative 1/2. Move that over, it becomes negative, divide by 2, and this becomes a positive 2. So x would be all real numbers, but x cannot be a negative 1/2 or a 2. And that's what they have down here. Okay? Lots of steps to show you what's going on item by item. Now, so far we have just been simplifying rational expressions. And how about if we're going to multiply? Well, the rules for multiplication is you multiply the numerators, you multiply the denominators. And again, your denominators cannot be zeros. So if we had something like this, we would just multiply, and notice nothing can be cross-canceled here. So it's just going to be 24 over 55. And then here, theoretically, you put parentheses around there, distribute, and it would look like so. Now, keep in mind also that where normally you would distribute, they're going to ask you here to leave it in factored form. Simplify, but leave in factored form. So let's try some examples here. Bring it up so you can see it. Now, normally don't overwrite what I'm doing, but save time and room. I can see I can cancel out this 5 with this 5. I can cancel this 2 with this 4 and I get a 2. And I can cancel out one of the A's with this, so I end up with that. So what do I have left on top? I have a to the second over 2. Now for this one, in order to do it, and we can think of this being over 1, I'm going to have to factor this. And I do a lot of factoring in class, and I will do a lot of factoring in those work additional exercise booklets where I do some of these. And they have it all worked out here, so I'm not going to repeat it. But again, this is over 1. So we factor this. This is already factored. You factor the bottom, which is, by the way, a perfect square trinomial. And then now you look for those factors that are exactly the same. This one will factor with this one, and that's about it. So your final answer then, and you leave it in factored form, is what we have here. Now, some of them get challenging. For instance, this one you may or may not remember from chapter 5. This is the difference of perfect cubes. So that will factor into that special factorization of the difference of perfect cubes. And then you start canceling out wherever you can. And somewhere in here, they're taking, oh, there's the -1 there. You see you have these sort of reversed. If you want to reverse that and make that an A -1, you have to take out a -1. Again, that's pretty tricky to reverse those terms, those variable and a constant there. So now that will cancel out with what you have on the bottom. But that -1 is still in there. And you cancel out some of the a to the second with a to the second. You're left with an a to the third, which is going to be a negative. And that is your answer. Now, some of you may have put this in a different way. For instance, if I were doing this, I might say, well, let me factor out a -1 already and make this a to the third -1. Now, when you factor that, you get, in essence, the same thing as we have here, but the a squared would be here. But again, that should give you full credit, and on a test, of course, I would give you full credit if you did it this way. So they're going to ask some challenging things as you do this. Now here we're going to take a look at division of fractions. And as we look at division of fractions, one of the terms we need to be reviewed on is the reciprocal. Now, what is the reciprocal? Well, it's just taking, if you had A over B, the reciprocal of that would be B over A, so that if you multiplied it, it would equal a +1. So reciprocal, even though it's a little bit challenging, you just take the denominator to the numerator to the denominator. And keeping in mind something like this is over 1 anyway, we don't write it, but when we do the reciprocal, we have to do that. Now, why is that important? Well, in Math 100, we said whenever we have division of fractions, which is what this is, we convert the division of fractions to multiplication of fractions, and we do so by taking the reciprocal of the second term. Notice here it's C over D. Here it becomes, after we change it to multiplication, D over C. So it's not really a lot of division. We're changing all division of fractions to multiplication. Let's try one. Again, I could write it out. I do that often in those examples I spoke of. But here it's written out nicely. A division of radical expressions. We're going to change this division to multiplication by taking the reciprocal of this second term, flipping it over, and there's nothing to cancel out, so that is our answer. Leave it in factored form. Now they do get a little more challenging. Here we have in function notation. We're going to convert that. Let's have it all written out down here somewhere. We're going to convert this to multiplication right there. We're going to take the reciprocal of this term, and now we start factoring. Lots of factoring. And again, it takes time. You could make one little error in a sign somewhere, and that could really mess you up. But when you finish, this is what you get. Now, an interesting point here, when you are defining your domain, you have to also consider this one. And, well, this one's already in the domain, but before you change it to multiplication where this goes on the top, you also have to take this one. So a positive 2 is going to be in the group down there, right there. So again, lots of stuff, and just this one problem may take 5-10 minutes, maybe not so long, depending on your level of mastery, but you need to know the process of what's going on there. Okay, another thing we introduce at this stage is what is called the vertical asymptote. So let me go over this with you. Now, when we defined this problem as example 1 earlier in the lesson, we said that for t could be any real number, but t could not be a negative 5/2. Well, negative 5/2, when we put it on a graph like this, that is sort of the fraction that would, or the item that would make this a 0 in our denominator. That is called the vertical asymptote. So that when you solve denominators, and we'd have something here and we say x cannot be 3 or x cannot be whatever, x cannot be 0, That is the vertical asymptote. Okay? That's what is described here. Now, they're tying it into a calculator. Again, we're not requiring that, but if you have one, you might take a look at it. This is what it looks like if we imagine that line in there. Normally, that line is not going to appear. And they do give us some other questions that we're going to skip. And here they want us to, and what they're showing in the previous example, we have to tie a little bit of it here. If you think of this and you simplify this, finally, after it's simplified, and you find out what value makes your denominator a 0, that will be your vertical asymptote. That is, if a function is described by a simplified, that is after you canceled out those common factors, then whatever value makes that denominator a 0, that is your vertical asymptote. So as we look here, what does it look like our vertical asymptote is? Apparently for this one. Well, it's going to be, our denominator, remember, would be in simplified form equals 0. This just factors out, and we get x equals 1. So our vertical asymptote will be 1 right there. And in a graphing calculator, it doesn't show the vertical asymptote. Okay, I think we're just about finished in this section. Yep. Now they do give another visualizing for success. Here this is x equals -2. And I noticed on one of the others I was off a little bit because it was so tiny I couldn't read it very well. Here this is an inequality where y is going to be greater than something. Now our slope is over 1.5. Again, I'm not going to try to guesstimate, but this is an interesting little review. This one we know. This is going to be y is 1 over x, I believe. Let me see. There it is right there. And this is your parabola, and this is y is less than or equal to. And it looks like a 1 and a 1. And I would think that this one is, not studying it a lot, but y is less than or equal to, solid line, of our slope, which is a positive 1, x plus 1. Okay. And again, if you go in your textbook to A23, which is the an alternate animated version of this activity, My Math Lab, well, whatever. It's supposed to be on that page in the addendum to this, but we don't know. Okay, we'll wind this up.